Any questions, first of all, technically or logistically, from anybody? Okay. The homework number 2 is due next class. Okay. The class after that, so it's due on Thursday. Thursday, you won't be getting another homework. Instead, you're assuming our computers work. You will be getting a take-home exam, okay, to work on for the next week. So don't worry about that. Particularly, it'll be an open book kind of exam. But that hopefully will go back. The first one, I believe, is due to go out on Thursday. Am I correct, or is this news to anyone? Okay, good. So that's true. Sometime in the near future, I'm also going to pass out just a list of graduate projects. Today, the printer broke, or the day the systems were down, and I couldn't process my document. But you may get that either next class or the class afterwards, and we'll talk about that. Don't worry about that. The other logistical announcement is that I'm having the first pizza with the prof on not this Thursday, but next Thursday. So I don't feel I've been doing a very good job of meeting many of you. And so what I will do is I have a sign-up sheet outside my office. There's room for 10 people there. Thursday at noon, not this Thursday, but next Thursday at noon, the 25th, I believe it is, I will have pizza for the 10 people who sign up. And so if you're interested in getting, we'll sit at noon, we'll talk about whatever you want to talk about, except the take-home exam, which will be due later that day. But about other things, I'm happy to talk. And if you're interested, I encourage you to go sign up on the sheet outside my door. Any questions about the pizza issues? At some point, I may try to have an Ademco pizza, but we'll discuss that later on. Any questions? Okay. In that case, let's get started on the next topic, which is congruences. And this is going to be helpful. Had some questions about some of the homework problems, and I think this material will be helpful for some of you who've been confused with those homework problems. And what a congruence is useful for, among other things, is answering questions such as, what is the last digit of a number? So let's say we have the number 10 to the 1,000th. What is the last digit of 10 to the 1,000th? Okay. 0. Okay, everyone says, yes, that's obviously 0. But why is it obviously 0? Okay, that's really what the issue that we want to get into. And my claim is that using our congruence notation, the reason is, or an equivalent statement to the fact is that 10 to the 1, the last digit of 10 to the 1,000th is 0. It's really saying that 10 to the 1,000th is congruent to 0 mod 10. You read the 3 horizontal lines as being congruent, okay? And what the congruence notation basically says is that A is congruent to B mod M is equivalent to saying that M divides A minus B, okay? So what this is useful for is that it enables us to describe one reason, there are a lot of useful things about congruence notation and dealing with congruences. One thing is that it enables us to somehow partition the integers into classes whose remainder is the same, okay, mod something. So if we consider the equation, x is congruent to 1 mod m, what is that? That, in some sense, describes all the numbers. If we have a fixed m, this is really an equation that specifies all the integers such that that integer minus x minus 1 is divisible by m. So what does that mean? That really specifies all the integers whose remainder, when you divide it by m, is 1. Correct? If we say that x minus 1 is divisible by m, okay, well, that's basically what we're really saying here. That means that the remainder of x divided by m is 1. Okay? And so if you want to think about what the congruence notation means, when you say that A is congruent to B mod m, what you're really saying is that A mod m, okay, is equal to B mod m. Again, that mod is now being used in the notation of the remainder when we divide it by. Okay? Any questions about that? Okay? So congruences are going to be useful in lots of contexts. Why is it useful with respect to the digit problem? Well, let's go back to this thing. If you think about it, when we take a number and take it mod 10, I claim that the remainder, that a number mod 10 is going to tell you the value of the last digit of that number. Correct? Because if you take a number and divide it by 10, the remainder, if you write a number in base 10, this shouldn't be news. It's going to be 10 to the 0 times something plus 10 to the 1 times something plus 10 to the something bigger than 1. That means everything except the last digit is, when you that number, everything except the last digit is clearly a multiple of 10. Okay? And so really what we want to now know is when we want to know what the last digit is, that's the equivalent of asking what is this number mod 10. Okay? Any questions about that? Okay? So fortunately about congruences do observe some laws that make them nice to work with. And so we can start to answer some less trivial questions. Like what is the last digit of 9 to the 1,000th? Okay? Is there anybody who can do that one in their head? Okay? Okay? Turns out actually you probably could do this in your head. Okay? Once you know about congruences. Okay? Well, how would I do this? Okay? Well, one thing I would like to claim is that 9 is congruent to minus 1 mod 10. Why? Because again, all the numbers that are that are m apart are congruent to each other. Okay, by definition. So clearly 9 is congruent to minus 1 mod 10. My claim is that if the following law of multiplication of congruences holds, then in fact, that if we could show, normally if you show that A is equal to B, then A to the n is equal to B to the n. Okay? If we can do such a thing with congruences, it's a lot easier to multiply minus 1 to the 1,000th than it is to multiply 9 to the 1,000th. Okay? My claim is in fact that the following identity on congruences holds. If A is congruent to B mod m, and C is congruent to D mod m, then A times C is congruent to B times D mod m. Okay? This basically says that if you have two congruences, you can mod the same with the same modulus. You can multiply them together. Why is that? Well, I claim that A times C minus BD is going to be equal to, okay, we could make this, if we add and subtract BC from both sides, here. Here, if we look at what I've done, I've subtracted a BC here, when I have A minus B times C. Here I have a B, I'm adding a BC, okay. This equality certainly holds. Okay, is there anybody who's skeptical about that? Just added and subtracted BC here. If so, what do I now know? I know that M divides B minus C, A minus B. Why? Because that's what this says. Okay, that when you say a congruence, A congruent to B mod M, what you're really saying is that A minus B is divisible by M. Okay? Likewise, if we have a congruence C minus D, we know that M divides C minus D. Okay? So now what do we know here? I know that M divides this. Okay? And if I have something that, if this is M times something, clearly M divides that. This is going to be B times M times something. Okay? If M divides both parts of it, M divides the sum of it. And so really what we've proven is that given that M divides that and M divides that, clearly M divides AC, M has to divide this. Okay? Because this is equal to that. We've shown that M divides both parts of that. Saying that M divides AC minus BD is exactly the same as saying that AC minus BD, AC is congruent to BD mod M. Okay? And so I claim we've just proven that we can multiply moduluses Multiply congruences if the modulus is the same. Any questions about that? Okay. Good. So what this means is now it becomes easier to see what the last digit of 9 to the 1,000th is. Okay. Why? We've shown that 9 is congruent to minus 1 mod 10. Therefore, I know that 9 is congruent. Therefore, 9 squared is congruent to minus 1 squared. Therefore, 9 to the 1,000th is congruent to minus 1 to the 1,000th. It is minus 1 to the 1,000th. Okay? Well, that's 1. Okay? So my claim is that 9 to the 1,000th mod 10 is 1 mod 10. Therefore, the last digit of 9 to the 1,000th has to be 1. Okay? Any questions about that? Okay? If, in fact, 1,000 was an odd number, like let's say 1,001, then we would have that the last digit of 9 to the 1,000th would be minus 1, which may seem suspicious, except that minus 1 is just another name for 9 when we talk at mod 10. So what this tells us is we now know what happens to the last digit of 9 to the whatever. Okay, it alternates between 1 and 9 forever and ever. Okay, which if you should be able to verify by working something out. Any questions about that? Okay, it showed how, again, because we now know that we can multiply congruences, it gives us power. Here we use the special case that if A is congruent to B mod M, A to the N is congruent to B to the N mod M. Okay, any questions? Okay, good. And again, you can play these kind of tricks quite a bit. What is 2 to the 741 mod 5? Okay? Again, this is the kind of thing that, you can actually do these kind of calculations almost in your head. I would observe that, again, 2 times 2 is 4. 4 is congruent to minus 1 mod 5. Okay? So again, we could write this expression as 2 to the 740 could be written as 2 times 2 to the 741, I could write as 2 times 2 to the 740, correct? By just pulling 1 out. Then this says that I can sort of have the exponent, okay? And this is therefore then going to be, without doing any arithmetic, it should be clear that 2 to the 741 is equal to 2 times 4 to the 370. Okay? 4 to the 370 is, mod 5 is minus 1 to the 370. This is 2 times minus 1. That's 2 mod 5. Okay? And though, lo and behold, again, you can work that kind of thing out easily. Okay? Any questions? So if you want to think about playing around with these things, the easiest things to work for are when you can sort of show that your thing is going to be congruent, something to 0 or 1 or minus 1. Okay, and then those are the easiest things to play with. Any questions? What is the last digit of 2 to the 753 in decimal? Well, now we want to know what is this mod 10, okay, before we showed it mod 5. And again, in this case, it's not quite so easy to move back and forth. But I was able to observe that 2 to the 3 mod 10 is 8. 8 is minus 2. Minus 2 cubed mod 10 is minus 8, which is in fact equal to 2. Okay, does everybody agree with that? So what could we do? We could take a look at this thing, divide the exponent by 3, chop it down so that this is the same as minus 2. This happens to be a multiple of 3, so it divided equally. Once we now had this exponent, it's no longer a power of 2. Okay, I could pull out, if I subtract 2 from 241 minus 2 is going to be a multiple of 3. Okay, I can factor out 2 to the 2 and keep chopping it down until, lo and behold, you can figure out what that number actually is. Okay? Just armed with this law, it is kind of impressive that something that simple enables you to work with such large numbers so easily. Okay, and this gives you one out of the reasons why working with congruences is important in computation. Any questions about the congruences so far? What they mean, what the rule is? Question?
Just repeat this 2 to 753. I don't get how you get minus 2 there.
Question is, how did I go from 2 to the 753 being equal to, is congruent to minus 2 to the 251? Well, one thing I notice is that 7, if I add up 7, 5, and 3, what do I get? That's 15. 15 is divisible by 3. Okay? So one thing that's a cute trick, which in fact you can prove with congruences, that any number, any integer, if the sum of the digits is 3, it's divisible by 3. Most of you have probably seen that. So I know that in fact if I divide this by 3, I get an integer, which is 241, right? So I can write 2 to the 753 as 2 to the 3 to the 251, correct? That 2 to the 3, that basically I'm using the observation that, which is, okay, 2 to the x to the y is equal to 2 to the x times y, okay? And so basically what I did was I converted this to that because I knew that 2 to the 3, I knew what it was. 2 to the 3 is minus 2. So lo and behold, I've lowered the exponent and replaced it by this. Okay, and that's really what I did. Any other questions? Okay, good. So what other examples of congruences can we work with? Okay. What is the value of 2 to the 573 plus 3 to the 752 mod 7? Okay. My claim is I've shown you now how to compute this to the mod 7. Okay, or basically should be convinced that you can hack on this pretty easily. I've shown how to compute that mod 7. We talked about how we can multiply congruences. In fact, we can also add congruences. Okay? So what I claim is, in fact, if we know that A is congruent to B mod M and C is congruent to D mod M, then in fact A plus C is congruent to B plus D mod M, and A minus C is congruent to B minus D mod M. Okay? That in fact you can both add and subtract congruences. Why is that true? Well, again, the proof is very simple. We know that M divides A minus B if A is congruent to B mod M. We know M divides C minus D if C is congruent to D mod M. Therefore, I claim that if M divides this and M divides that, then M divides the sum of them. Okay? And if we now want to simply repackage these things, move A plus C here and B plus D here, this says basically that M divides A plus C minus B plus D. And this is exactly the definition of what it means to say that A plus C is congruent to B plus D mod M. Okay? Any questions about that? You can add congruences. You can multiply congruences. You can subtract congruences. Okay? Any questions about that? And again, so here we could, for the problem above, again, it's nothing too hard. We could have independently worked out what 2 to the 573rd is mod M, mod 7. Worked out what that is mod 7. We know that this is 1 mod 7, this is 2 mod 7. The sum, therefore, is 3 mod 7. Okay? Any questions? Now, you have addition and subtraction and multiplication of congruences. The only tricky thing is you don't quite have division. Okay? So, for example, let's say that we have 3 times 2 is congruent to 5 times 2 mod 4. Okay? One possibility would be to say if we could have division, as we said before, then that would argue that we could cancel on this thing. Okay? And so that would argue that 3 is congruent to 5 mod 4. 3 is congruent, 3 is congruent to 3 mod 4. 5 is congruent to 1 mod 4. Okay? So this shows that you can't just cancel things out. Okay? You got to be a little bit more careful about that. Okay? Any questions about that? Okay? It turns out that whether you can cancel or not depends upon whether or not the divisor that you're trying to cancel by is relatively prime to the modulus or not. Okay, that turns out to be the critical issue between whether or not you can divide or not. Okay, so what do I claim? I claim that that A times D is congruent. If A times D is congruent to B times D mod M, that would imply that A is congruent to B mod M if and only if D is relatively prime to M. What does relatively prime mean? Okay, in terms of the greatest common divisor. Okay, D is relatively prime to M if the greatest common divisor of D and M is 1, correct? Okay, and my claim is under those conditions you can in fact divide. Why is that? Well, let's look at the proof. We know that if D is relatively prime to M, then in fact that means the greatest common divisor of D and M is 1. Okay? We showed last time that as a byproduct of our Euclidean algorithm, we could show that if the greatest common that for the greatest common divisor of D and M, there were integers D prime and M prime, such that D prime times D plus M prime times M was equal to 1. That was sort of the byproduct we showed last time. So what can we do? We know we're starting out with AD is congruent to BD. Multiplying both sides by the same thing isn't going to change the congruences, because we know that D prime is congruent to D prime. Okay, and we showed we could multiply congruences. Okay, so we know that AD D prime is congruent to BD D prime. The other thing we know is that D prime, by definition over here, is equal to 1 minus D. Okay, that what do we know here? My claim is that we know that D prime, M prime, is going to be equal, M times M prime is going to be equal to 1 minus D times D prime. Correct? We just move that term over. How do we interpret this as being? We know that M times M prime is a multiple of M. It's congruent to 0 mod M. So if this is going to be equal to, we know that 1 is congruent to 1, that 1 is congruent to 1 mod M. We know that if 1 minus this is going to leave us something that is going to be a multiple of M, then we know that D times D prime has to be congruent to 1 mod M. Okay, think about this. This may be a little bit tricky. Okay, we know that this is a multiple of M. We know that 1, okay, is, when you divide something by M, it's going to be a remainder of 1. 1 minus this thing, the only way we can get something to be divisible by M on this side is if we divided this by M and we had a remainder of 1. That's exactly what this is saying. Okay, that D times D prime is congruent to 1 mod M because of that. Any questions about that? How many people see what I mean? See why that is true? How many people are lost or a little lost? Okay, couple people. Okay, what are we saying here? This is an identity. Okay, this is an equality that we know before. We now want to think about what happens when we divide both sides by M. M prime divided by M, you divide it by M, you get an integer, right? 1 minus D prime, you divide it by M, you darn well better get an integer, okay, because it's the same thing as on the other side. What does it mean to get an integer here? Okay? It means that when we divide, this is going to be, when we divide 1 by m, the remainder we're going to get is 1. Okay? Minus something. If this is going to work out so that it divides evenly by m, then in fact the remainder of d prime d, when you divide it by m, has to be 1. And that's an equivalent way of stating that is that d prime is congruent to 1 mod m. Okay? Any questions? It's important about how you have to know how to, it's simple once you know how to read what this congruences mean. Okay? So it's important to know what the notation is. Okay? Any questions? So now we're basically at the punchline. We now know that a d prime, okay, d, we know we're interested in what is a times d prime mod m. Well, we know that d prime is congruent to 1 mod m. We can multiply this, okay, sort of because of the multiplication law, we can replace this by its identity. A times 1 mod m is a mod m. It's congruent to a mod m. And b times 1 mod m is congruent to b mod m. So what do we know? We know that that ADD, okay, what we were trying to prove. We were trying to prove that this, okay, that given this, it reduced to that. Well, we saw that this is congruent to A, okay, that this thing is congruent to A, this thing is congruent to B, okay, there in fact, we know that this was equal to that, okay, but here we showed that by multiplying it, given this, we showed that this was equal to that. We showed that this was equal to that, and we showed that this was equal to that, therefore this has to be equal to that. Okay? And lo and behold, A has to be congruent to B mod M. Okay? Any questions? If in fact, okay, they are relatively prime, the modulus, yes, question. Here's the punchline. Let me try that. Okay? What did we show up here? We showed that starting out from A congruent to D, AD congruent to BD mod M, we showed that ADD prime is congruent to BDD prime. Okay, that's just by multiplying it. We have this up here. Down here we showed that ADD prime was congruent to A. Okay, and BDD prime was congruent to B. So what do we have? We know that this has to be equal to this because of that. Okay? We know that this has to be equal to that because of this. And we know that this has to be equal to that because of this. So lo and behold, that means that A is congruent to B mod M. Okay, this is substitutions of the equalities. Okay? Any questions about it? Okay, how people sort of see this? Okay? How people don't see it? Okay? No one will admit either way. Okay? On one level, it's just algebra. Okay? And so you can look at that and convince yourself one way or another. Okay? The important thing to see here is that, in fact, this is true if D is relatively prime to the modulus. Okay? Now, the other thing to see here is that if, that in fact, the other way, okay, that if in fact we have, that if we're not relatively prime to the modulus, okay, what happens if we have something that it divides both, we have something that divides both the left-hand side, the right-hand side on the modulus? This, I claim, under these conditions, we can in fact cancel. Okay? So suppose, let's say we have AD is congruent to BD mod MD. What does this read? Well, this says that AD minus BD is congruent to MD, over MD, perfectly divides, correct? If this is an integer, clearly, by dividing top and bottom by D, we get this. This is equal to that without anything. Okay? So in fact, if we have something that we can factor in all three terms, this clearly implies that. Okay? How many people believe that? Okay? People don't believe it. Okay? Again, it's sort of that if this is an integer, then multiplying top and bottom by 1, it's still an integer, right? That's exactly what we're doing here. And likewise, so here, if this is an integer, we can multiply top and bottom and get this. This is going to be equal to that. And this is just a restatement of that. This is just a restatement of that. So we get the following interesting thing. If the thing that we want to divide is relatively prime to the modulus, then in fact we can cancel it up, in here. If it's not relatively prime to the modulus, we can then cancel across all three. Okay? Any questions? Let's look at the previous example. In the previous example, we had trouble when I tried to divide by canceling across here. 3 times 2 congruent to 5 times 2 mod 4. Okay? But in fact, now you'll see what's true. Since all of these things are multiples of 2, I claim it is true that 3 is congruent to 5 mod 2. What is 3 mod 2? And what is 5 mod 2? 1. Okay? So in fact, if we have something that's a product of all three, we can cancel across it. Otherwise, we don't. Okay? And so the summary is, okay, that our real law of division of congruences looks something like this. Okay? If you think about it, that when D is relatively prime to M, you can divide by D without affecting the modulus. And when D does divide M, okay, then in fact you can divide D across all three. So what I claim actually is that AD is congruent to BD mod M is equivalent to saying that A is congruent to B mod M over the greatest common divisor of M and D. Correct? Because any part that of any factor that D and M have in common divides all three terms. And so you have to cancel it out and also lower the modulus. Anything factor of D that is not in common with M, okay, you can cancel out from here without affecting the modulus. Okay? Because the key observation is that D divided by the greatest common divisor of M and D, by definition, has to be relatively prime to M. Okay? Any questions about that? Okay? It gives us a law for working with congruences. All right, so we can add, we can subtract, we can multiply, and we can almost divide. Any questions? Good. Using just these laws, we can prove some interesting things. Okay? In fact, we can even prove Fermat's theorem. Okay? How many of you have ever heard of Fermat's theorem? Okay, everybody's heard of Fermat's theorem. Okay, I will now give you a proof of Fermat's theorem. Okay? And it's in the context of, actually, this is a proof that turns out to be important in algorithms. Okay, the notion of algorithms for factoring or testing whether a number is prime. Now, normally, if you wanted to test, if I ask you if 56 is a prime number, how would you test it? Okay, what would you do algorithmically? What's the simplest algorithm to test whether a number is a prime? Does anyone want to propose an algorithm? Okay. Someone asks you to write an algorithm to test whether a number is prime, what would you do? Okay. A number is prime if it does not have any factor except 1 in itself. So one possibility is to say, here is your number n, divide it by 2. Is its remainder 0? If it is, the number is not prime. Okay, otherwise, it might still be prime. So try all possible divisors. Okay, the possible interesting divisors are the ones that lie between 2 and the number minus 1. So my claim is one way to test whether a number is prime is to do a linear number of divisions. Okay? How many people understand what I'm talking about? And how many people are confused? Okay? No one admits to being confused. So it should be easy to see that, in fact, by doing a lot of division, you can test whether or not a number is prime. Okay? In fact, you can do a little bit less division than I said you could. Okay? if a number is not prime, my claim is it has to have a factor that is less than the, if a number n is not prime, my claim is it has to have a factor that is less than the square root of n. Can anybody tell me why that is? Okay. Because my claim is that if you take the smallest number, okay, I mean, it's basically the thing. If you think about the smallest interesting prime factor, you divide it by n, you're going to get a number that's going to be greater than it. If it's the smallest interesting factor, the factor when you divide it by n is going to be bigger. Okay? That will be true unless the only number you have is a perfect square. If your number is a perfect square, then the smallest factor will in fact also be the largest sort of interesting factor. Okay? And so we know that the smallest factor of any number has to be less than or equal to the square root of n. So by doing square root n divisions, you can be done and show that the number is prime. That's good, except that the square root of n is very, very slow. Is a large number if n is large. If I ask you to tell me whether or not a 200-digit number is prime, and you insist on trying the square, what's the square root of a 200-digit number? It's something like a 100-digit number, right? Okay? So if you want to go through all 100-digit numbers, and then tell me if any of them are factors, you'll be there for a long time. In fact, the right way to test whether a number is prime, a high-speed way, involves an idea of using some interesting number theory to create a randomized algorithm for this. Okay? The better idea is to find some property which holds true for all primes. Okay? And then test this property several times to see whether it is true for your particular number. Okay? Suppose every prime is has a nice personality. Okay, let's think of it this way. You go and you ask the prime something. If it answers politely, it might be a prime. You ask it something else, it answers politely, it might be a prime. You ask it something else and it flips you off, you know that could not have been a prime number because all prime numbers were polite. Okay? That's the idea of the randomized testing. We want to find some kind of property that is true for all primes, okay? Okay? But sometimes not true for something that's prime. Okay? Or specifically, find some property that differs between the two of them. This property that's commonly used, okay, the most common of those properties, is something called Fermat's theorem. Not Fermat's last theorem. That's the one that you heard that was required several hundred years to prove. This, in fact, is one that we will prove in the lecture. Okay? It's Fermat's little theorem is what it's often called. Okay? Fermat's little theorem says that n to the p minus 1 is congruent to 1 mod p if n is relatively prime to p. Okay? So n to the p minus 1 is, if you divide it by p, the remainder is going to be 1. Okay? And this is true for any n that is relatively prime to p. Okay? Now, suppose we know that p is a prime, okay, and we try an n less than p. Okay? If p is a prime number and n is a number smaller than p, is n relatively prime to p? The answer is there's nothing, assuming it's greater than 1, okay, I mean, in which case it's still relatively prime to it, okay? So my claim is any number n that is less than p is going to be, if p is prime, is relatively prime to it. Okay, how many people agree with that? Okay, how many people are confused or don't agree with that? Okay, good. So how could we test whether or not 753 is a prime number? Okay? Well, my claim is, if 753 was prime, what would we know? We could put p equals 753, p minus 1 or 752. The claim would be that for any n raised to that power, the remainder would be exactly 1 if you divided it by that. If, in fact, p was prime. Now, that is an amazing property. Let's stop and think about it. N some reasonably large n to some reasonably large p, what are the possible values the remainder could take on when you divide it by p? What's the smallest possible remainder? 0. What's the largest possible remainder? P minus 1. If this was really a random remainder, let's stop and think about it. It's not quite random, but intuitively, if it was a random remainder, the odds that it happened to be exactly 1 would be something like 1 out of p. It'd be a rare thing for that to just happen by chance. Okay? People see what the logic is? That it's sort of like, if you're sort of betting, if I pick a random n less than b, what are the chances that I raise it to this? It just happens to have a remainder of 1. Not that good. But on the other hand, Fermat proved that if it was a prime, if p is a prime, then in fact, for any n that's relatively prime to it, this remainder is going to be 1. Okay? So what is the idea? I can try picking random values of n and plug it in. If I come in, I plug in n, take n to the p minus 1, figure out that residue mod p, and that residue came out to be 56, what do I know about p? Then p could not have been prime. Okay? If I have a candidate prime, okay, in fact, like 753 I claim is not prime. Okay, it's obviously prime. It's divisible by 3, right? But if you now take a look at which values of n will in fact, when you plug it in there, will in fact be congruent to 1. Well, 1 to the 752 is indeed 1 mod, congruent to 1 mod 753. In fact, there's only 4 values of n which magically happen to hit that number. So what is the idea of the algorithm? If you want to tell me, here I've got a prime number, okay, what I'm going to do is I'm going to guess a value of n randomly, plug it in. If it comes back and it says that it's congruent to 1 mod m, p, I'll say, maybe you do have a prime number. I'm then going to pick another value of n. Come back, if it comes back to 1 mod m, okay, 1 mod p, then maybe you do have, that's even more reason to believe you're right. I can play this game as many times as I want till I trust you. And my claim is I shouldn't have to play it very many times until I do trust you. Okay? So, because if in fact it was a non-prime, most of the times, or at least half of the times you can prove, okay, you will actually end up, this test would fail. And this gives us a fast way to test whether or not a number is prime, because this amazing property holds for prime numbers. Any questions about that? Any questions about the algorithm or the idea? It's really an amazing randomized algorithm. Okay, one of the earliest and most important such algorithms. But it hinges on the fact that this is true for any prime number, for any prime p, and any n relatively prime to it. Okay? How do we prove that? So we want to prove that n to the p minus 1 is congruent to 1 mod p, if n is relatively prime to p, for all prime p. I tell you the proof of this is very, very simple if you give me a fact, which I'll then prove. Okay? And this fact is actually very, very useful on its own right. Suppose I consider the numbers n mod p, 2n mod p, 3n mod p, up to p minus 1 mod p. Okay? How many numbers are those going to describe? How many numbers did I write down here? This set of numbers. Okay? N mod p, 2n mod p, 3n mod p, up to p minus 1 n mod p. How many numbers are there? Okay? I've just given you a description, a set of p minus 1 numbers. My claim actually is that all of those numbers are distinct. Okay? That none of those, first of all, what's the range of those numbers? What's the biggest number value that n mod p could be? P minus 1, right? Could any of these numbers, if the p is prime, could any of these numbers be 0? Okay? Could it be the case that some number smaller than n, smaller than p, okay, or that 2 times some number smaller than p is congruent, it's a 0 mod p? No, because p is a prime, okay? So if so, you'd be giving me a new way to factor it. So what I'm really saying here is that in fact these set of p minus 1 numbers that you get from this, in fact, there's only p minus 1 possibilities because none of them can be 0. The interesting thing is I'm going to claim each one of these occurs every number from 1 to p minus 1 occurs as a residue mod p exactly once in that series. Okay? See some eyebrows being raised. Okay? If that's true, I claim that this problem, the result falls easily. Why? Well, let's think about what we have. I know that if I multiply all the things on the left side, I'll know that n is congruent to something mod p, 2n is congruent to something else mod p, 3n is congruent to something yet else mod p. Suppose I multiply those p minus 1 congruences together. On one side, I'm going to have n times 2n times 3n dot 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 up to pn minus 1 n. On the other side, if they're all distinct, I'm going to have 1 times 2 times 3. The order of these numbers might differ. It might be 56, 32, 196, 1, 2, 4. But if in fact each one of these numbers from 1 to p minus 1 occurs exactly once, then the product of all of them, I claim, is going to be p minus 1 factorial. How many people are with me so far? How many people are not with me? Okay? Questions? Okay? Well, if that's true, let's take a look at this thing. This is going to be, I could factor this as being p minus 1 factorial times n to the p, okay, is congruent to p minus 1 factorial mod p. We know that each one of these, if p is a prime number, p minus 1 factorial, okay, is relatively prime to p. Why? Because each one of its factors is relatively prime to p. Okay? So, lo and behold, I could cancel both sides, okay, and I have that n to the p minus 1 is congruent to 1 mod p. Okay? Any questions? It should be clear that if in fact I get this permutation, I have just proven Fermat's little theorem. Any questions about that? Or comments one way or another? The more amazing thing is, why do I get that permutation? And again, I urge you to work out some examples to show yourself that this is true, because it's kind of an amazing thing. For example, what if we consider p is 7, a prime number. We now try 1, okay? What if we consider n, this is going to be, let's just stop to think about it. For p equals, this is going to be, if n is 1, it's going to be 1 times 1, 2 times 1, 3 times 1, okay? I claim that we indeed get, obviously, the numbers 0 to 7, 0 to 6 mod 7. Does everybody agree with that? What about for n equals 2? Well, 0 times 2 is going to be 2 mod 7. Okay, 0 times 2 is going to be 0 mod 7. It should be 0, 2, 4, 6, 8. 8 is 1 mod 7. 3, 5. Lo and behold, you see it counts the even numbers and the odd numbers. For n equals 3, 3, 6, 9, lo and behold, it works. But why does it work? Okay. Suppose it didn't. Let's now use a proof or contradiction. Suppose it was true that the series of numbers kn mod b did not describe a permutation for k goes between 0 and okay, what you call it? 0 and p minus 1. We know that there's going to be p minus 1 values here. Okay. If there is a contradiction to this, if in fact they did not describe all unique values, it had to be that somewhere there was a repetition. Correct? Okay. Because there's only p minus 1, there's only p possibilities here. There's only p possibilities for the remainder. If in fact these numbers were not unique, then lo and behold, okay, it would have to be the case that there were two numbers, okay, a and b, two values of k, let's say a and b, such that a times n was congruent to b times n mod m. So the only way you could skip a number is if you had a duplicate, okay? And so therefore there has to be a congruent to b mod n, okay, an congruent to bn mod b, for some a less than b, both within these brackets. But what do we know? By our division rule, we can divide by an, bn, we can divide both of these by n if we divide the modulus by the greatest common divisor of p and n. But if n is relatively prime to p, okay, then this has to be 1. And so, lo and behold, a is congruent. This means that a is congruent to p mod b, which is a contradiction to say that there's two different values of k. Okay? Because lo and behold, we only had two values. If a is congruent to b mod b, the only way that it could be, if an a not be equal to b, would be if they differed by p. We don't allow any two numbers that differ by p. So lo and behold, a would have to be b. We have a contradiction. Okay? And so the punchline is, okay, and it's an interesting punchline. If c is relatively prime to m, cx mod m will give distinct values for all x between 0 and m minus 1. Okay? Any questions about that? Okay? It's a surprising property, but turns out to be very, very useful. Okay, and I'll in fact show you an application right now. Any questions? Okay. Well, one application of it that I stumbled across once was in Professor Kaufman has, over the years has built various parallel architectures for trying to do graphics rendering. Okay. And in one of these incantations, somewhere in it appeared the following congruence. Okay? K is equal to, okay, or congruent to, if you want to think of it, 5x plus 3y plus z mod 517. Where on earth would that equation come from? Okay? Well, suppose, let's say, again, what Professor Kaufman does is this volumetric graphic stuff, okay, where he's assuming that you've got a sort of cubic grid of memory cells, okay, and inside each bit you've got a little bit of a number that represents how much stuff is there, and you do various things on this memory, and that's how they do their graphics. Now, if you've got n by n by n memory cells, okay, doing anything on something that big would require n cubed time, because there's n cubed memory cells. So it'd be nice if you could do something in parallel. Okay? So what they want to do is the following. They'd like to take their n by n by n cube of memory and stick it in to n, those elements into n different memories, or a little bit more than n different memories, with the property that whenever you do a common operation, all the elements that you're interested in are in different memories. What would happen if you wanted to do an operation and all the operations were in one memory? How much parallelism could you do? Okay? Well, I can't get at the data in parallel. Okay? I can only get one thing out of each memory at one time. So if I have 512 processors, let's say, okay, I could do 512 things if you give me 512 things, okay, to do. But if they're all sitting in one of these memories, you can't get it out, okay? And so the goal is to try to find a way to stick these n-cubed memory cells, n-cubed elements, into n different, or basically n different collections, such that all the interesting access patterns have the property that each element is going to be in a different, each element you want to access lies in a different memory. How many people see why this is a desirable thing? Okay? A couple people. How many people don't see why this is a desirable thing? A few more people. Good. Okay, let's just go through the example. So, suppose, let's try to do this in 2 dimensions. Let's say that I have a memory like this, and I want to be able to stick these things into, let's say, 4 memories. Let's start it. Let's say I want to put these cells into, let's say, 4 memories to start with. Let's call these things 1, 2, 3, 4. 1, 2, 3, 4. Okay? How would you recommend putting these elements? Let's say I'm going to want to be able to access them according to rows and columns. That's a thing to want to do with a matrix, right? You want to cruise down a row or cruise down a column. So what could you do? One thing you could do is to say, well, I'll put element 1, 1 in there, 1, 2 in there, 1, 3 in there, 1, 4 in there, 2, 1 in here, 2, 2 in there, 2, 3 in there, 2, 4 in there, 3, 1 in there, 3, 2 in there, 3, 3, 3, 4. Now I've got 4 memories. Each one of these, in fact, contains that column's worth of things. If I wanted to access a row in parallel, could I do that? Sure. This element here is in this memory. This element here is in that memory. This element is in that memory. This element is in that memory. If I want to access in a row, ka-chunk, 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 it's easy to process, right? But what happens if you now want to access a column? Now you're in trouble, right? Because all the elements of that column, okay, are stuck in one memory. And you got to dribble it out one element at a time. Wouldn't it be nice if we could find a way to take each one of these elements, element ij, map it to a memory, such that each memory element, each common access pattern, for each common access pattern, the cells you want were in different memories. Then you could spit out and work with it fast. Okay? Any questions about that? So this is a dumb way to do it, but this, it turns out, is a smarter way to do it. Okay? Suppose, let's say, in our 512 by 512 by 512 memory, cubic memory, we take the property that we map element x, y, z to memory, to position x times 5 plus 3 times y plus z mod 517. Each element is going to get a number from 1 to 517. From if you want to think of it 0 to 5, it's 516. Okay? What is an interesting thing about 517? Can anybody guess what's an interesting thing about 517? It's prime. The other thing that's interesting about it is it's bigger than 512, right? Okay, but not a lot bigger. Okay? So now what are we going to try to do? We want to now access memory cells in common patterns. What are the common patterns? Well, the most common patterns, I think we'll agree. We go bop, 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 bop along a row, bop, 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 bop up a column, or bop, 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 bop across an axle. Okay? Well, what happens if we do that? Let's think what the congruence here is. Okay? We've got that K is this mod 517. We map these things here. My claim is, if we look at this thing, if we're going to consider a row or column, okay, or a either a row or a column or an axle, we want to consider a set of elements, okay, such that the 512 elements, where two of these things are held fixed and the other one varies, correct? That's what really it means to access all the elements in a row or a column, or a row or a column or an axle, is you're holding two of those coordinates fixed and the other one's counting through. Well, what do we know? We know 1 is relatively prime to this, 3 is relatively prime to this, 5 is relatively prime to this. Okay? My claim, therefore, is, if you think what's actually going to be happening, if x and y are the ones held fixed, we're then going to be considering really some junk, which is x and y being held, okay, fixed, plus z, which is going to be iterating through each time, okay, times the appropriate constant. What's going to be ended up reduced to is there's some junk, okay, the two fixed dimensions will reduce to a constant, okay, when you multiply it by the appropriate weight up here. X and y, if x and y are always being held fixed, if x is 1 and y is 2, well, 5 times 1 and 3 times 2 is going to be the same regardless of what z is, right? So lo and behold, we've got the situation where we've got a constant plus some c times some number that's counting, where we know that c is relatively prime to m. So what does that mean? That means that we know, because c is relatively prime to the modulus, based on what we just did, for the numbers from 1 to 512, all of these are going to be assigned to different buckets. This d that we're adding is just an offset. It means to take all the numbers and add d to them. That's not going to make any two of them equal, right? If I'm different, if you have more money than I do, and somebody gives each of us $5, you still have more money than I do, okay? But we certainly don't have the same amount, even if we take it mod m. Maybe I now have more money because you may have been cut down, but we're still not going to be equal, okay? So my claim is that for any orthogonal query, a row, column, or axle, okay, in fact, all the elements will be in different memories. How many people see that? How many people don't see that who want to see it? A couple people, okay? So basically what I've just done is, we know that, let's take a look at the example. Let's say that I'm interested in, I have a cube here, which is, I'll draw badly. Let's say I consider the elements projected back from cell 36, 56, whatever. I'm now talking about all points. I want to now get access to all points 36, 56, x, where x ranges from 1 to 512. Okay? What happens when I plug it into this congruence here? Okay? This is going to mean that I'm going to be getting the congruence 5 times 36 plus 3 times 56 plus, in this case, z, mod 512, 517. Certainly I showed that z mod 517 as z goes from 1 to 512. Clearly those all take on different values, right? Let's make it a little bit easier. Let's say that this was z, in fact, let's make it, let's say that I wanted to go through instead and do this, but this was 56. This would be 1. This would be 3. I know 3 is relatively prime to 517. Therefore, by what I showed you before, 3 times 1, 3 times 2, 3 times 3, dot, 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 3 times 516. All of those would describe different numbers, mod 517. So certainly the numbers 1 through 512 will be in different numbers. So this hashing scheme has popped them all into different memories. Any questions? Question?
You can take other constants for x, y, and z as long as it's prime to 517, right?
So the goal here was, okay, that you could in fact pick for what I just showed you to do. So long as these constants were relatively prime to 517, then in fact it would give you what you wanted. Okay? But in fact, these constants have some other properties that make them interesting. For example, another thing you might want to do in a matrix is cruise a diagonal. Okay? That you might just not only want to cruise, go up a row or a column, but go through a diagonal. Well, what is a diagonal? Or at least a major diagonal? That's one where you have some kind of offset. And now all of the numbers, okay, increment by k instead of 1. That means that you're going sort of back in, through some kind of a diagonal. But lo and behold, a similar thing is going to happen. Okay, once you fix that in there, then again, you work through what the equations will work out. Lo and behold, you're going to get a constant times something times k. Here the k is depending upon which direction you want, as far as positive or negative or whatnot. The coefficients of whether you go up or down or whatever may make these things plus or minus 1. The interesting thing is that these diagonal numbers were selected so that any sum or difference, okay, combination of this is also going to be relatively prime to it. And that enables you to cruise diagonals as well. Okay? Any questions? So these kind of ideas come up quite often whenever you're talking about mapping something to something else. Using some kind of a congruence is a common business in hashing, in mapping things to parallel processes, and lots of different things. And like I say, the fact that modular arithmetic works out well, has this permutation property, can be useful just like it was here. Any questions about that? Okay. Another place this stuff may be useful for is on the last couple of homework problems. So think about that, and I guess I'll see you guys on Thursday. Okay, unless there's any questions. Okay, thanks a lot. I'll see you guys on Thursday.